let's start. Hello. This talk will be about TLS testing, and the speaker is Hubert Kario. He works at the QE security team, and it's going to be a very interesting talk, so let's dive into it.
Now? Oh, okay. So hello. My name is Hubert Kario, and I'm working at Red Hat as the security engineer for TLS libraries, basically OpenSSL, NSS, and GNU TLS. And today we'll be talking about how the testing of TLS looks like in basically all operating systems. So 2014, few things happened. Basically, every big cryptographic library had some critical vulnerability. And the biggest one of them probably was Heartbleed, which was a bug in OpenSSL handling of rarely used function of TLS protocol. The other issue in OpenSSL was handling of change cipher specification message. It was accepted when it shouldn't be. The other was the gotofail from Apple. They didn't actually check signatures of Diffie-Hellman key exchange. On the other hand, NSS and GNU TLS had various problems with certificate verification. In case of GNU TLS, it considered some certificates to actually be CA certificates when it didn't have extensions, while in case of NSS, it didn't verify signatures correctly. So invalid signatures were considered correct, and actually the most severe one was a bug in S-channel, also known as WinShock. And it was a vulnerability which allowed the attacker to execute arbitrary code if the server was running SSL, any kind of implementation, either if it was just HTTP server or mail server or anything like that. And it also was a problem client side, but of course that is a bit harder to exploit. So why this stuff happens when we are testing TLS, aren't we? Yeah. Let's be frank, there is a lot of legacy code out there. And by legacy code, I don't actually mean code that is old or that's spaghetti code. I mean code which isn't actually properly tested. It doesn't have proper code coverage. It doesn't have proper unit testing. And why is that? If I have code which is not unit tested, I actually don't know if this code works at all. I mean, who here haven't seen code committed to repository which shouldn't even reproduce any kind of sensible values? Well, multiple times. On the other hand, if I have a bug in code, then it's if I have a bug in code, it's hard to refactor. I don't know what part of the way the code behaves is the expected and what is the side effect. So if I have a unit test for the code, I can actually say this is the expected behavior, this is the not expected behavior, and as such can verify that the addition don't break the existing behavior. So, a study in 2011 took a look at many open source projects. At open source projects, and less than 20% of them actually use any kind of test planning. Only 40% use some kind of test tool, either a framework or some kind of automation. Just under 50% use code coverage for the testing that they do. On the other hand, other studies took a look at many critical problems which caused data loss in distributed file systems, and just 8% of the bugs they found were actually caused by bugs in logic. 92% of the errors, of the problems, of the lost data were caused by missing or incorrect error handling. So by that I mean error handling which was just to do, or logging, and we need to do something better with that, and so on. On the other hand, of those bugs, 77 could be easily reproduced using unit tests, and the other 23% were mostly in a project that didn't have any kind of tooling for automation of unit tests. So that's mostly the reason why they couldn't verify the fixes using unit testing. So how do TLS libraries compare to that? Not well. OpenSSL basically doesn't follow any kind of good practice. It has very few tests, and it doesn't do much error checking in the tests. GNU TLS is not much better. It just adds a framework for testing, and NSS is quite good compared to them. It uses a framework, it has quite a few negative tests in unit testing, and it has well, a large number here we see. Well, let's compare it to some other pieces of code. SQLite has about 97,000 lines of code. At the same time, they have 10 million test cases, which means that for every test, every line of code, we have 103 test cases run. And by that I mean they have 100% branch coverage. They run the tests under different circumstances, like under Valgrind, under other memory checker. They use fault injection for the test, and so on. So we don't really see our other libraries, so let's zoom a bit. Okay, let's zoom by a factor of 10 again. So we now see NSS, and by decent test coverage here, I mean test coverage that for every 8 lines of code, we have 1 test case. So that means code coverage for of 1/8 for a line of code. NSS has about 670,000 lines of code, so its coverage is about 0.01 per line of code. To actually see OpenSSL and GNU TLS, we would have to zoom by 3 orders of magnitude still. So why is this so bad? I mean, why we don't do much more testing? The problems are multiple. X.509 and ASN.1, that's stuff that gives nightmares to people that actually understand them, and they consider it arcane. For other people, those are binary blobs, we don't care. So that's the reality. Thankfully, it's quite easy to fuzz using existing fuzzers, and it's quite extensively tested and attacked by researchers. So most of the bugs in these areas are already found, and verified. On the other hand, we have a lot of invisible bugs in TLS implementations. For example, by timing the responses from the server, we actually can decrypt or at least guess with high probability what the encrypted data was, or what the private keys that the server used for encrypting the data were. That is the Lucky 13 issue, that's the beast, and so on. On the other hand, if we have a library and we want to do the actual testing, that's not really easy. Most of the libraries have multiple checks so that they don't send bad data. Libraries don't like sending bad data. That means that for testing, we actually need something that can reproduce like 99% of TLS implementation to be able to generate like the other side of conversation in TLS. And lastly, TLS is very hard to fuzz using automated tools. This is caused by multiple problems. TLS is a very stateful protocol, and the state that is needed to be kept is quite large. Additionally, most of the data is checksummed, encrypted, so this needs, after fuzzing, the data needs to actually be post-processed quite significantly to be able to verify the other, the behavior of the server or client under test. So basically, a combination of hard problem and understaffed project. Until very recently, OpenSSL had 1.5 developers. So how we can fix this problem in a systemic way, so that we can fix all those free and possibly other implementations. Of course, we don't want to duplicate our effort. We don't want to actually go inside OpenSSL and start writing unit tests because we will just lose ourselves. The nice things about TLS is that the client needs to advertise actually what it supports, all the features of the protocol it supports. On the other hand, the server can select only those features which the client actually advertised. So we can, in the case of the client, we can just look at the data it sends us and see, yeah, this client supports this, and this. And on the hand of the server, we can actually probe it using a few hundred connections and then recreate the full feature set that the server supports. So we can create a single test tool which will know what the server supports and as such create the test cases for the specific server because it knows what are the responses for a given implementation, for given feature. So I looked at existing network fuzzers, and most of them are focused on fuzzing files, which for network protocols it's quite different. At the other hand, there exist network protocol fuzzers. The two that were most promising are Sully and Scapy. Unfortunately, both suffer from exact same problem. It's very hard to keep the state of the TLS connection in them. And they both have very minimal support for any kind of cryptographic operations on those packets after they are generated. At the same time, on the other hand, Sully actually doesn't support for the test case to look what the server response were for each and every query. So I cannot actually do a full handshake because I don't get the responses from the server. So basically all the existing ones are useless for TLS testing. While I'll be now talking about fuzzing, by fuzzing here I will be meaning testing, the fuzzer itself will actually understand, needs to understand the protocol. So it knows that if I'm inserting an extension which isn't yet defined, then the server should ignore it. If I'm adding values which are not defined, the server should also ignore it for cipher, for example, for ciphers. So, if we take a look at a full TLS handshake, it's quite a lot of messages sent between client and server. The most important part here is that when I'm sending client hello and I'm changing values in client hello, in some cases, to verify that the server actually rejected the message, I need to wait for the finished message from server and verify that I cannot decrypt it correctly or the result of decryption is incorrect. In case of RSA handshake, so that's the simplest one and the most commonly used, the client advertises its features, the server selects the features from the client using the server hello. The certificate is the server's public key and the X.509 certificate, and since that I'm done, there will be no messages from me. The client key exchange uses the public key of the server and encrypts information so that only the server can decrypt it, and this is the information used to select the key for rest of the transmission. Chain cipher spec means that further communication will be encrypted, and it sends a finished message that cryptographically binds all the previous messages that it sent and received from the server. The server does something very similar, sends information that it will encrypt the further messages and sends its finished message which cryptographically bind all the previous handshake messages. Now, if I want to test what happens if the client key exchange contains a pre-master secret, that's the cryptographic key that's used then to get the keys for the actual encryption, the server must actually encrypt, use a different kind of data, randomly generated data for generation of the finished message, so that it's hard for the attacker to guess what kind of information, what kind of private key is used used by the server. On the other hand, if I am working as a server and I'm testing a client and send server key exchange which has wrong signature on the parameters which are sent by the server, I'm not expecting to actually see client key exchange because the client should abort this connection here and there. So when I see that the connection is successful, then I know that the client misbehaves. That's actually the bug in Apple's secure transport. So that's the gotofail. If, on the other hand, the client starts to send messages which were not, which the server doesn't expect. For example, here when I'm inserting certificate message, the correct implementation would do that only when the server requested for the certificate. If I'm inserting messages which are not expected by the server should abort the connection and with the message that the handshake failed or something like that. If it doesn't, then for example, in S channel, so the Microsoft vulnerability, the problem was that it did accept, and because it accepted and actually parsed, all the servers were vulnerable to the problem in parsing the certificate. Not only those servers which which actually used the client-based certificate authentication. So, on the other hand, if we insert a chain cipher spec here, then we will be able to reproduce the OpenSSL CCS bug. And again, the correct behavior here would be aborting the connection by the server. So, I've started working on a tool that will allow either to easily test this kind of conversation, or would actually enable us to generate automatically test cases, and most importantly, the negative test cases, so that the server behaves correctly even if the client doesn't, or vice versa. Unfortunately, recently I've noticed that the previous implementation won't work with some advanced features, so I had to scrap everything and start anew. So this is the planned architecture. Basically, the server starts, the fuzzer starts with probing the server, generates the test cases, and the test cases are expected to pass. Then the fuzzer is injecting information to the conversation, to the example conversation, where the conversation has both the client side and expected messages from the server. So the fuzzer starts inserting messages or modifying the messages and sees if the server behavior changes. And this way, when the executor gets the conversation, it can actually see if the server behaves as is expected from the standard, or if it misbehaves, and that should be then fixed. The actual parser and marshaller for the TLS messages is a TLS library, which is pure TLS. TLS implementation in pure Python. So the nice thing is that it has basically the only dependency of the fuzzer is the Python interpreter itself. So and it runs in Python 2.6 up to 3.4, the latest version. I think it's 3.4.1. For now, I'll be focusing on servers. That's because they represent much bigger attack surface, and they are also a bit easier to automate, but the goal is to have a tool that will be able to test both server and client. And the end goal is to have a system which will be a drop-in addition to continuous integration system, where you tell it you start the server in this way using this command line, and try to break it, and adding higher fuzzing ratio, for example, that it needs to test much more different values, would allow us to run a longer fuzzing session, not aimed at just verification of the current implementation. And that's basically it. You can find the project at GitHub. So if you have any ideas, for example, for the test cases you would like to see tested, or the kind of modification you would like to see, I will more than welcome any bug reports like that. And I think that's all. Questions? Yes. Yes.
Does that mean you're focusing on testing servers then?
Yes.
TLS fuzzer acts as a client?
The question was if by testing server I mean that the fuzzer works as a client. Yes, that's the case. So I'll be able to accept even some information like the server is at this IP, try to break it, and it should work just fine. For now, I'll be working with just start this command, and this will generate you a server on localhost with this port, but that's trivial to extend to external servers. Yes?
What's it written in? What's the license, etc.?
So what's the license? I'm planning to do it in GNU GPL2. But the underlying the TLS Lite is BSD.
How big is that library? Small enough I could have a copy of it in the NSS tree so that we can run it upstream?
The question is if it's small. The library is small. The TLS Lite at this moment is, I think, about 20,000 lines of code. So it's very, very small. And as I said, it has no external dependencies, so it should be fairly simple to just add to a code repository and start using it. Yes?
Would you detect that, for example, in some case, the server should quit the connection because you send it wrong data, but you don't recognize that the server crashed, actually.
So the question is how I'm detecting if the connection was aborted because the server crashed, or because or just it was aborted because error from my side. The simple answer is I don't, because if I'm sending a message, I'm starting a connection and see that it disconnected, and it disconnected at unexpected time, because the conversation will have also the expected values from the server, which includes stuff like disconnection. For example, the Microsoft implementation doesn't send alerts, but just disconnect. So that's one of the reasons why I would like to have that. And but on the other hand, if I'm running the server locally, then it will be actually run inside of the TLS fuzzer. So I can just look if it crashes and not, and just log that it crashed at this time, and when running this command. How I'm going to investigate when it crashed? The idea is to have it run using a completely deterministic random number generator, so that I will be able to reproduce the whole fuzzing session, and then start from like last run, and if it doesn't, then start going backwards. Yes?
Maybe in some later stage of the project you might be interested in so-called symbolic executor, which is basically interpreter which introspects the code you are running, in your case the SSL server, and it helps you to generate the test case, because you know that this branch of code will be entered if the input is this. So, but it's kind of experimental technique.
So the question is if I'm going to use symbolic.
It's more recommendation.
Symbolic executor for checking if the code is actually executed. So basically branch coverage. I'll be able to check and generate data which will actually enforce, check both sides of the data. That's actually quite hard because most of the crypto code runs in using constant time algorithms. That means that it actually does calculation which will then either output 0 or 1, depending on the failure or pass of the test. So this isn't a regular if this then and so on. So I don't think it would be relatively easy to actually test it like that. Okay, so if there are no more questions, then I think I'll let you go. And have a nice rest of the weekend.
Hi, Hubert.
Hi.
I'm Tomasz Mraz.
Hi.
So nice to meet
Yeah.
you. Know, with sending you these data.